In this video, I'm going to walk you through how to prepare an input file for the magma chamber simulator. So we're going to do this for a fractional crystallization run. For other runs, including AFC, RFC, and RAFC runs, we'll do further tutorials so you can learn to use it first for an FC only, and then get more complex as you progress with the magma chamber simulator. If you have not installed the MCS on your system, please close out this video and refer to our other tutorial on installation of the MCS and the folder structure. Or if you're at our workshop, you can go ahead and ask one of us for assistance. So the first thing we need to do is open up our input file. To get to that, we need to navigate to our Finder, then our Documents folder, and then to the MCS folder. Input files are located intuitively in the folder labeled Input and Output. We're going to select the input file labeled MES_FC_1. This is an input file for a fractional crystallization only run. So let me make it just a little bit bigger so everybody can see what is going on. And this first thing that you'll see here in the input file is this blue box. The blue box are system variables that get globally applied to all subsystems. The magma chamber simulator is comprised of 3 different subsystems: the magma composition, the wall rock composition, and any recharge compositions. So those all have separate inputs, and then these system variables globally apply to all of them. This is just for convenience, so you don't have to type in pressure for each composition or oxygen fugacity for each subsystem. It's just a lot easier to put things in at once, and it's a lot less confusing. The first variable you'll see here in row 2 is FM0. This is the minimum mass fraction of liquid that must accumulate in the wall rock in order to trigger assimilation. So in this case, we don't want AFC, we don't want any assimilation, and we're going to set FM0 to 1. Essentially what we're doing is telling the magma chamber simulator to melt all of the wall rock that we have before assimilation can be triggered. This is not realistic, and we're never ever going to have enough heat to do that, so we're going to set our FM0 at 1. The next variable we have is excluded phases. These are phases that are excluded from all 3 subsystems. An easy way to input these excluded phases is actually to do it directly from the magma chamber simulator interface. So to get to that, we can go back to our Finder, navigate to the MCS VBL code folder, and open up our MCS file. We're going to enable macros, and you'll see that there's a lot of different buttons here. In a later tutorial, I'll walk you through how to actually do a simulation. So right now, we're really only concerned with this bottom button that says Excluded Phase Help. If we click on that, you bring up a user form. And that user form has a list of different mineral phases that can be excluded from all 3 subsystems. So say, for example, we want to exclude spinel and tritomite from our runs. We can make sure that those boxes have been checked and click on Copy to Clipboard. This actually will automatically close the user form, and go ahead and exit out of the magma chamber simulator. Remember, press Don't Save. Once we've done that, we can go back and click on cell B3 and Command V to paste. So you'll notice that spinel and tritomite are now input in this cell, and they're separated by a caret. So if you want to type things in by hand, you're obviously more than welcome to do so. Make sure that your mineral phase names are A, correctly spelled, B in lowercase, and C separated by a caret. Otherwise, the magma chamber simulator won't be able to recognize them and won't be able to exclude them from all the different subsystems. The next variable that we have is system pressure. It's fairly self-explanatory, and it's given in bars. So for this run, we want to actually set our pressure for all 3 subsystems to 2.5 kilobars. So I'm going to type in 2,500 bars. The next parameter that we have is enthalpy convergence steps. This is the number of steps that occur in an isenthalpic calculation, and those happen during AFC, RFC, or RAFC runs. Right now, we don't have that because we're doing an FC only run, but the magma chamber simulator still does need a value. So general ranges for these values range from 10 to 100, but through rigorous testing, we found that the sweet spot is 30. I highly recommend that you stick with that, but of course, you're welcome to play around with the number of convergence steps. The last global system variable is oxygen fugacity. So in column F, we've put some little helpful hints that you can refer to if you're not sure exactly what to do, and texts that might help you to select the proper variable. So for oxygen fugacity, you'll notice here that I have NNO input in this cell. And that's because for this run, I want to run along the nickel-nickel oxide buffer. You'll also notice that NNO is in lowercase. If you want to change the oxygen fugacity buffer, or if you want to run at FO2 absent, different parameters that you can input are here in column F. So we have none, FMQ, COH, NNO, IW, and HM. And these are the same standard oxygen fugacity buffers that you'll find in standalone melts. So now we can move on to the magma composition. It's important to note that the total sum of the major oxides should be normalized to 100 prior to a simulation. So perhaps the input composition that you're running might be given in a publication where things don't normalize to 100. Or you already have a normalized composition, but you're adding in additional water. So you do need to renormalize those values. We do have a little renormalization schematic built into our input files. In column F on the right-hand side, there is a series of numbers. You can go ahead and fill in your composition in column F, and then the renormalized output will be given here in column G. You can then copy that composition, go back to column B, and paste it in. I actually go ahead and do paste special and paste the values because the magma chamber simulator doesn't like it if you just do Command V. The next parameter that we have for the magma composition is the starting temperature. Now it doesn't really matter what you actually put in here. I try to put in a temperature close to the liquidus, and that's because in the magma chamber simulator, whatever the magma composition is will always start at the liquidus temperature. You can't just start fractionally crystallizing the magma at a random given temperature. It must start from the liquidus temperature. So I would say we're going to go ahead and we'll input 1570. So what will happen is melts will kind of navigate from 1570 degrees to find the liquidus temperature. I like to put a temperature that's pretty close to the liquidus. It can be above or below though, but I do tend to run every composition through standalone melts first, just to figure out where the liquidus and solidus are. You should probably make this a pretty common practice because it avoids having to redo a lot of runs because maybe one composition isn't quite right or you're not really sure what the solidus temperature is for a wall rock composition. So as a good practice, again, I highly suggest running everything through standalone melts first just to see the different parameters. So for an FC only run, you could just run it through melts, but we're going to run it through the MCS because, well, that's what this tutorial is for. So the temperature decrement is the number of degrees in between each equilibration step. So for example, let's say the liquidus temperature is 1500 degrees for this composition. If I put in a temperature decrement of 20, the next equilibration step that's output is 1480 degrees. After that, the magma composition will cool another 20 degrees to 1460 degrees and so on and so forth. So the magma chamber simulator is slated to stop a simulation when the magma composition and the wall rock have thermally equilibrated. And that can take a really long time depending on the mass of the wall rock, the starting temperature, the wall rock and magma compositions, your wall rock composition, lots of parameters. So if you're like me and you're really only interested in things that happen at higher temperatures, you're not too concerned about what happens when things start to kind of equilibrate, I like to use this hard stop temperature. That's in row 31, and that's the next parameter. We've built this in. It's really convenient because if you let the MCS run to equilibration, things can take a really long time. So for this run, say I'm only interested in stuff that happens before the magma composition reaches, say, 800 degrees. So I'm going to go ahead and input 800 degrees as my hard stop temperature. All right, and we're finished with our magma. So now we can move on to our wall rock composition. Wall rock composition is given in orange. And again, you want to put in something that you've already run through melt standalone first so that you can figure out a temperature that's pretty close to the liquidus and then a temperature that's just below the solidus. And I'll explain why shortly. So because I'm trying to turn off assimilation, I like to use compositions that are even more mafic than whatever my magma composition is. That way it's really, really, really hard to assimilate. I try to make it as difficult as possible to get any liquid buildup within the wall rock composition. So I have an even more mafic basalt here. And again, this might not sum precisely to 100, so you go to the right, check your composition. renormalize it, and then paste it back. So the reason why using standalone melts to evaluate your wall rock composition is a good thing is because this is where things can get very finicky. When you prime the wall rock, even though we're doing FC only and you don't really need to use the wall rock for anything, the MCS still requires that you prime it, and it needs to know where the solidus and liquidus are for the wall rock composition. So if you're not really concerned with assimilation at all, I find one good composition and I stick with it. Obviously, if you are assimilating, then you need to have whatever your necessary parameters are. But I already know that these parameters work and it will run without a problem in any version of standalone melts. And personally, I'm not the assimilation gal. So somebody else is going to do assimilation. I just leave this as it is. So for the ending temperature for this magma composition, for the wall rock composition, I'm going to go ahead and put 799 degrees. Right? I've already run this through melts. I know that the temperature is below the solidus. The temperature decrement that I've set is 25 degrees. That's because, again, I'm not assimilating during the wall rock prime. I don't want this to take very long, so I put a larger temperature decrement. The start temperature for the wall rock fine solidus, I tend to put that just above where I know the liquidus is. Again, I've run this composition through standalone melts. For the initial wall rock solid mass, I make that a really, really, really large number. Remember, we've set our FM 0 to 1 to make sure that MCS will melt 100% of the wall rock before assimilation is triggered. By making the wall rock an unreasonably large mass, we're just triple ensuring that we're not going to have any assimilation here. And then the last parameter for your wall rock subsystem is wall rock initial temperature. So when your simulation actually begins, this is the temperature of the wall rock. This is going to go up during your run. So again, another way to turn off assimilation is to make the wall rock initial temperature very, very, very low. So right here, we're going to say, 400 degrees. That's low enough, and I can tell you right now there won't be any assimilation during this run. So the next thing we're going to do is navigate down here to the recharge composition. The recharge compositions are given in light blue. You'll notice, or the first one's given in light blue. You'll notice that there's actually 5 of them. MCS can do up to 5 recharge events at once, but again, we're doing FC only. We're not concerned with recharge at all, and we want to go ahead and turn it off. You do have to input some composition, but you want to make sure to turn it off. So here, underneath the composition, make sure that these 4 cells are completely blank. So this input file, actually, you should have already received it. It should have been pre-populated, so you don't need to go through all of these steps when you're doing your first fractional crystallization only run. This is more of just a tutorial. Say you're starting from scratch or you want to change things again. So this concludes our tutorial on how to create an input file for a fractional crystallization only run. In our next tutorial, we'll learn how to fill out an input file for assimilation. So we're going to be doing an AFC, or assimilation and fractional crystallization run.